Chris, you're still muted.
Okay, am I muted now?
No, you're good. Thank you.
Okay, very good. Thank you, Deb. So the beautiful thing about being in this time of COVID, right, is that we are all learning how to use technology every single day, no matter how many times we've used it in the past. So with that being said, I hope you guys are all doing really well. I am speaking to you from North Carolina, Asheville, North Carolina, where I am a professor at the University of Mars Hill. And actually, I'm not a professor as much anymore since I've taken on a new role of the director for the Center for Engaged Teaching and Learning here on campus. But still, my favorite thing to do is to work with my students and work with teachers across the U.S. and talking about mathematics. So welcome, everyone. I'm going to go ahead and start by sharing my PowerPoint here. Okay. So I hope everyone can see the PowerPoint. We're going to talk about making sense of math through fractions.
We can't see your PowerPoint just yet. Did you hit the share screen?
I have shared the PowerPoint. Okay, so Deb, there is something else going on here. Hold on one second.
Go ahead and try again. I just changed a setting.
Okay. So Deb, are you still there?
Yes, I am still here.
Right, so let's try to share that PowerPoint again. It worked just fine a few moments ago.
It did indeed.
We're going to try it again. It's the beautiful thing about technology and the beautiful thing about teaching is, especially with this group of teachers, we all have to be super flexible. So let's try it again. And in 3, 2, I'm waiting for it to open. All right, here we go. Now it's open. Right. Can we see the PowerPoint now?
Yes, we can. Thank you.
Awesome. Thank you, guys. All right. All right. So again, the title of this presentation is Making Sense of the Math Through Fractions. And a lot of times we think, well, that's a horrible idea, right? Why would we want to use fractions to make sense of anything? Because fractions are hard. They're tough. They are something that most of us aren't comfortable with. And with Halloween approaching, I'm always thinking about my youngest daughter. Several years ago, she came out of her bedroom and she had on this sheet and with holes, and I thought, oh, she's a ghost. And then I noticed on the sheet she had 1/2 written on her sheet, and I asked her, I said, I don't understand. Are you like a half sister? What's going on? And she said, no, Daddy, I'm a fraction. Everybody's afraid of me. And so I think that does a great job of summing up how a lot of kids feel about fractions. So we're going to talk about fractions today. And I understand that you may not be teaching some of the content we talk about with your particular group of students, but the bottom line is, in order to teach any group of students, we have to have a better understanding of how fractions work and how they serve us on the number system. So to give you a little bit of context, the PISA is the Program for International Student Assessment. And this is how the US in general ranked in the PISA assessment. So the US ranked 3rd in the Organization of Economic and Corporate Development countries per capita GDP, meaning our gross domestic product. So basically what that little block is saying is that we are the 3rd richest country out of the OECD sample. We ranked 4th in the amount of money we spend on our students. which is also really interesting. So we're the fourth richest, we spend the fourth most, and our students look very similar to the average range from the OECD sample. So there are students from disadvantaged backgrounds with severe multiple disabilities, with single parent families, low socioeconomic status. They look very similar to the students in the other countries in which PISA assesses. With that being said, this is a little bothersome that the US average score was 27th out of 34 countries, meaning that we are falling behind a lot of these other countries, even though we're the third richest and we spend the fourth most, which kind of tells us, hey, it's not about the money. That's not what is making the difference for these other countries. So what is making the difference? The NAEP assessment shows us that the percentage of students at or above proficiency level is 40% for fourth grade students and 33% for eighth grade students, and even less for those in high school. So in eighth grade, if we only have 33% of our students proficient at eighth grade math in the traditional classrooms, imagine how our students with significant disabilities are faring. Some of the things that we know happen in other countries that are higher performing than we are indicated here on this chart. The US teachers, we tend to focus most of our understanding for our students on learning terms and practicing procedures. We're very procedurally driven, where in the higher performing countries, and here we have them listed as Hong Kong, Singapore, Japan, they are more involved in helping students understand the problem solving that goes into the mathematics and less about learning the procedure. The pace, the US, we try to cover about 80% of their tested topics, where the other countries only cover about half of the tested topics, but they cover those half in such depth that it's applicable to the other topics on the test. Our curriculum, even with the Common Core, tends to go very wide, but not very deep, where the other countries, they spend time going in depth. And I think these last two statements really kind of sum it up. In the United States, the teachers plan by asking how they can get their students to get the answer to a problem. It's all about getting the correct answer through the correct procedure. In the other countries, they're spending their time and their planning through focusing on how they can use the mathematics that they're teaching to help students master mathematics they don't know yet. So it's not about getting the right answer. It's about developing understanding and conceptualization within the mathematics. Here we see some actual pictures that were taken in the TIM studies. And the TIM studies, they're called the International Math and Science Studies. And what they did is they went into these high-performing countries, okay? And we've got two pieces of data here. One from 95, where they looked at Japan, Germany, and the US. And they went in and they videotaped teachers teaching. And Japan was the high flyer. Germany was kind of in the middle, and the US was at the bottom here in 1995. And what they found is that the outcome of this, they said, was that teachers were connecting the math to the real world. Turns out that that really wasn't what was happening. It's a red herring. It sounds real, but that's really not what's happening. But those of us who were teaching in the classroom in 95, 96, 97, we'll remember things like the idea of classroom stores coming out and the ideas of checkbook registers popping up in our math books, where we're trying to connect it to the real world. And in 99, they did a more extensive study, and they found that their students still weren't excelling even with this connection to the real world. So they started to look at US, Japan, the Netherlands, Hong Kong, and the Czech Republic. And what they found, it was about connections, but it wasn't necessarily about connections to the real world. It was about connections to the mathematics. Okay. So I'm going to share a different thing, and I want us to think through what's happening here. Okay. So here is my little whiteboard, and I just want us to think about the procedures and what this does to us. So here we have, if I give you this problem of 2007 minus 9. In the United States, this is how we would solve that problem typically. We would say, well, I can't take 9 from 7, which is not true, but we would say we can't. And we have to borrow, which is also problematic because we're teaching them to basically steal because we're never giving this back. But I don't have any tens. I don't have any hundreds. I have a thousands. So that 2 becomes a 1. This becomes a 9. And sometimes we'll make it a 10 and then we'll make it a 9. And the same thing will happen here, a 10 and then a 9, and then this becomes a 17. So this is problematic in the sense that our students, if they weren't somewhat disabled before our instruction, they probably are now. Because this is nothing but a set of procedures to be memorized, and our kids who aren't good memorizers really struggle. In other countries, they wouldn't start here. Of course, they would start with, so if I had 53 plus 8, they would talk about 5 10s and 3 1s plus 8 1s. So I have 8 1s and 3 1s. That's 11 1s, and I can compose a 10. If I'm over here, if I'm over here and I'm doing 53 minus 8, if I compose the 10 here, I need to decompose a 10. So I can, if I have 5 10s, I would then have 4 10s, and that would give me 10 plus my 3. That's where my 13 would come from. The way that they speak about number here is really incredible. If I ask you how many ones we have in this number, the majority of us would say 3, but we don't. We have 53 ones here. We also have, if I ask you how many 10s, well, we have 5 full 10s, but we have another 3 tenths of a 10. I just need 7 more tenths and I would have another 10. If I gave you the number 253, well, I have 253 ones, 25 full 10s, or 25 and 3 tenths of another 10. Or I could say that I have 2 full 100s and 53 hundredths of another 100. So with that being said, when we look at this problem, those children who have this background and this understanding of the base 10 system approach this in a very different way. They would immediately start talking about decomposing the next highest value, which would be the 10s. In America, we look at this and we say, we have no 10s, there's no 10s, but we do have 10s. Here we have 200 10s because that is equal to 2,000. So 200 10s, if I take one of those 200 10s away, that leaves me with 199 10s. And then I have my 10 plus my 7 for my 17. What's interesting is that is exactly the same output that we got through this procedure. The only difference here, kids are happy. We have happy children because they understand where that 199 came from and they can see what it means to decompose. Up here, we have, this is what the teachers and the students look like. They're frustrated and they are really not sure how that happened. All they know is that that 2 should become a 1, the 0 should become a 9, and a 17, and it's buried in the procedure. With this being said, the high achieving countries, they are making connections, guys. They're making connections to the mathematics. However, in the United States, we're not making connections to the mathematics. We are teaching procedures, and that's where we spend most of our time. If I ask you, what is 4 squared? What is 4 squared? A lot of us would just say, oh, well, that's 4 times 4. Or, we also hear 4 times itself twice, or we go into the procedure of how to get the answer. So some of us may say 16, but then we have to talk about 16 what? If it's 4 squared, our output has to match our original unit. So 4 squared is 16 squared units, but what does that actually mean? And what is 4 squared? So we're going to do a lot of bouncing back and forth because I am a mathematician, so I need to write things out. So if I did this, 4, what is the base of 4 here? So my 4 to the power of 1, which means it's 4 in 1 dimension. So just like you saw in the PowerPoint there, it's 4 in linear fashion. 1, 2, 3, 4, right? So I have, oops, we need one more. 4. So it's 4 in linear fashion because it's in 1 dimension. 4 in 2 dimensions looks different, right? So 4 in 2 dimensions means that I have I have 4 in length and 4 in width. That's what that little subscript of 2 means there. That exponent says it's 2-dimensional. So I have 4 in 1 dimension and 4 in another dimension. So it's 2-dimensional. And I have 16 would be my unit of measure squared. So it's 16 squared units. When we are talking in terms of these connections that we as often educated, college-educated adults struggle with, these are all real for our students. They also struggle. If I ask you, what is the square root? What is the square root? Well, most of us would go back to our college math classes and try to remember the formula for square root. And I'm betting the majority of us can't remember that because it doesn't make a lot of sense until we talk about it in the terms that the square root is the root that this square grew from. This square grew from a root of 4. So it's the length of any side. So it's square root. I want to show you how these connections really matter over time for our students. So understanding 4 squared leads us later into the Pythagorean Theorem. Okay. And we'll do this rather quickly. So here is, let's talk about the Pythagorean Theorem. If I asked most adults what the Pythagorean Theorem was, they would say it is a squared plus b squared equals c squared. Well, that's the formula, but that's not really what it is. And some people will say, oh, well, I get it. It's that we have a right triangle, and it's because this is 90 degrees, right? Not because it's pointed to the left or the right there. So I have this triangle, and the most famous one that we all know is a 3, 4, 5 triangle. We'll label these A, B, and C. So if I take 3 squared, that means I make 3 in 2 dimensions. And that gives me 9 units squared. 4 in this dimension gives me 16 units squared. Well, what's interesting here is if I take these 9 units squared and the 16 units squared, and I add them up, that gets me 25 units squared. Well, in order for this 25 units squared to make sense, guys, I'm looking for this 5. I'm going to find the square's root. So I can divide this into squared units that are the same size as these. And that gives me 25 squared units. But here's what's interesting. If I look at the one side of that square, there are 5. units. So that's where my 3, 4, 5 comes from. But it isn't, this is not only used to find the hypotenuse. That's what we talk about. It's just like this equation, 2 plus 3 equals 5. If I take any of these out, I can find the other measurement. And that allows me to do this. This understanding is really important later on when we are working with ourselves, when we went through, say, algebra 2 and we were using the distance formula. Well, the distance formula is nothing more than the Pythagorean theorem. But here's the kicker. No matter what grade level I was in, the Pythagorean theorem did not tie back to squared units or the square roots. And the distance formula didn't square back to the Pythagorean theorem, and it should have, because I can see here's a right triangle, and the distance there is the hypotenuse of that right triangle. So my teachers spent all this time teaching me these things, but they did not make the connections between any of them. Without the connections, I'm kind of lost because everything is brand new and it's more and more to memorize. I imagine that a lot of us feel like math was just a set of memorization. And our students often feel that way too. So when we talk about our own understanding and instruction, we have to understand the math ourselves because we can't take students anywhere that we can't go. The better we understand the math, the better decisions we make when we are teaching the math to no matter what level our students are at. And in fact, I would argue that teachers who teach students who have significant disabilities need to understand the math probably more in a deeper, more connected manner than teachers who are not teaching this population, because we have to know all the different ways we can get to that answer because our students all get there differently. Lipping Ma said that the defining issue in implementation is the teacher's own understanding of the math. That if the teacher doesn't understand the math, getting the kids to implement the math is going to be incredibly difficult. And I would agree with that. We spend so much time with the significant population teaching things like time and money and simple geometry that we really don't go into depth often with what does the mathematics mean? And if we don't make a connection for those students on what the mathematics means, they're definitely not interested. It's a much harder sell for this group, this population. So if I ask you this, what is 6 divided by 2? What is 6 divided by 2? I'm going to give you just a second to think about it. And if you want, you can go ahead and put that on a piece of paper somewhere. Write it out. Most likely, most of us said, oh, well, 6 divided by 2 is 3, because that's what we were told. But is it really? Is 6 divided by 2 3? And if it is, where did the other 3 go? So if I have 6 items in front of me and I divide it by 2, that means I can do one of 2 things with it. It means that I can divide it. Let's say I have cups. So I have 6 cups and I divide them by 2 cup portions. That means that I have 3 servings of 2 cups, but not just 3, because these 3 servings of 2 cups, that's how I account for all 6 beans. It's not just 3. The same thing here. It may be that I have 6 cups of beans divided by 2 servings or 2 people. That means that I have 2 3-cup servings. Both ways, my answer is 3. But it's 3 with a lot more meaning. It's either 2 3-cup servings or 3 2-cup servings. This is where the idea of the unit is so critical. If I say 3, I have led my students down the wrong path. I have to help my students understand that 6 divided by 2, it depends on what I'm talking about. 6 cups divided by 2 cups gives me 3 2-cup servings. 6 cups divided by 2 servings gives me 3 cups in each of 2 servings. So this matters, especially when we have to show with the concrete. The key here is the language and the units that I'm giving. So if I ask you this, if I give you 3 ones plus 2 ones, most of us would say, oh, that's 5. But we have to be more specific. We have to say 5 what? 5 ones. The reason that's important is when I say 3 10s and 2 10s, if I say 5, that's a little more ambiguous. I need to say 5 10s. And sometimes teachers will say, oh, that's 50. And they just stop. They stop. But it's 50 ones. So when we get to things like 3 10s plus 2 ones, teachers will say 32. And I've done it. Before I knew better, this is how I taught. I would say 3 10s and 2 1s is 32. Any questions? And my students would be like, well, yes, I have lots of questions. I thought 3 plus 2 was 5. So wouldn't 3 10s and 2 1s be 5 twins? Well, no, it would not, actually. So when I say that 3 10s and 2 1s is 32, I have to put my unit there. 32 ones. And I know we're going to talk about fractions, but here's the point that I'm trying to make is that fractions are unitized. And we have to be able to talk about our units with fractions. This is where it starts. Later on, these units that we use in fractions come back to the same idea that 3 10s and 2 1s, I've got to have a common denomination. Denom means to name your unit. So a common denomination. So to put 3 10s and 2 1s together, I'm going to find a common denomination that those can be broken into, which in this case would be ones for 32 ones. That's no different than what we're doing with 3/6 and 2/5. I have to find a common denominator or denomination that these are broken into. These have to find a common denomination. So I find a common denominator. Kids in very early ages, they understand this. They understand that if I have 1 cow plus another cow, that's 2 cows. If I have 1 frog plus another frog, that's 2 frogs. But if I have a cow plus a frog, that is not 2 cow frogs. They understand this as 2 animals, 2 living things. Language and units matter. So we're going to take a section from Lifting Ma's book, and it's called Knowing and Teaching Elementary Mathematics. And this is all about elementary mathematics. If you have not read this book, I suggest you get it and you spend some quiet time in front of a fireplace with a nice glass of water or wine, whichever you prefer, and read this book because it's an amazing read. It's a hard read, but it's a good read. One of the problems that she presents here is this idea of division of fractions. And this is where we're going to spend our time talking about the unitization of fractions. I have 1 3/4 divided by a half. I want you to think about a story problem to show what's happening with this expression. So 1 3/4 divided by a half. I'm going to pause for 3 minutes and let you think about how you would solve this. And make sure you try, guys. Don't just say, oh, somebody else will come up with it. Go ahead and think through how you would solve this problem. Okay? What's a story problem that can show what's actually happening here, okay? 1 3/4 divided by a half. Go. You have a minute and a half left to process this problem. Okay, and time. When we divide, we think our answer should get smaller. What's interesting is that we're gonna spend a little bit of time talking about how we could deconstruct this lesson and help our students get a better understanding. What Ma did in her book is she compared how American teachers and Chinese teachers addressed questions to elementary math problems. What the American teachers did here, guys, is the majority of them flipped and multiplied. Often their answers did not match. And they confused division by 2 with division by 1/2. The Chinese teachers, however, they did something different. They gave a mathematically accurate story problem almost every time. And they explained the mathematics behind the operation, not just saying flip and multiply. And they gave multiple ways that this could be accomplished through the division of fractions. So what does it mean to divide by a fraction? Let's answer that. Here's a video. I want us to watch this together. Just kind of processing how we solve this as Americans. So I'm going to go ahead and I'm going to put 1 3/4 divided by 1/2. Okay. Ready? So what's the first thing we have to do? Change it, the mixed number into it. What's wrong? Why are you cringing? Okay, right, and when we talk about 1.75 divided by 0.5, I'm okay with that as long as we don't call it point, right? Because 1.75, that doesn't really have meaning, but 1 in 75 hundredths has a lot of meaning in it, doesn't it? And 50 hundredths has a lot of meaning in it, but 0.5, so yes, okay, so we could change it to a decimal. There's lots of ways, but the typical fashion in which we are taught to solve this is usually the improper fraction, or that, right? And I saw 3 people do it, this, right? And it's the weirdest thing. It's like the gang sign for math teachers. It's like, I don't know what it is, but it's just strange. So this is what we're gonna do, right? So let's talk about this first. So flip and multiply. Well, and making it this improper fraction. How many people, have seen this idea, right? Around the world is what some teachers call it. Well, that gets me 7/4. Where does 7/4 come from? Well, on the number line, I think it's really important that we explain why that is what it is. So here's our number line: halves and fourths, half-fourths. Here's how we get 7/4. So I have 1. That's 4/4. Does everybody agree with that? 1/4, 2/4, 3/4, 4/4. And then I have 3 more fourths. So there's 4/4, 5/4, 6/4, 7/4. That's where that number actually comes from. Is this number and this number equal? They are, right? And this is really a different form of that number. Would you agree? Okay. So 7/4. Now we get that 7/4. So I'm going to go ahead and do this. I have
or 1 3/4 divided by a half. And now I have 7/4 divided by a half. And then what do I have to do? Flip the second number and multiply. Why? Yeah, not to reason why. It doesn't matter, right? Yours is not to question why, only to flip and multiply. Good. So 7/4 times 2/1. And if we follow this through, 7 times 2 is 14. 4 times 1 is 4. This then can be reduced to what? 3 2/4, but eventually down to 3 1/2. This number is really confusing for a lot of our students because we're told when we divide, what should happen? It should get smaller. But oh my gosh, something happened here. This is a big deal. Would you not agree? This is a huge deal. So I have 3 1/2. What would happen? I'm just curious. If we didn't flip and multiply, I'm just curious. So 7 divided by 1 is 7. 4 divided by 2 is 1. It works nicely just because the denominators are divisible easily, but it would still work even if they weren't. You would end up with a decimal fraction, which would really scare kids, right? And children are scared of fractions. In fact, my youngest daughter, three years ago, dressed up as a fraction for Halloween. And I said, why? We don't have our units. And this is problematic. So let's spend a little bit of time, and we're going to come back to this, okay? But let's start to build an understanding of what's actually happening when I divide, okay? So if I have, I'm going to make a number line here. 2. We'll make sure it's a number line, not line segment. Are we good with that? So we're gonna use this idea of a bean party to start to play with this idea of division. So would you agree? Well, let me give you the context. My mom gives me 6 cups of beans, and she says, Chris, you can have a bean party. Okay. I have 6 cups of beans, but we're not going to the store. We're not going to buy any more beans. Okay. What you have, 6 cups, and that's all that you have. Okay. 6 cups of beans. So what happens, and I'm a really nice guy, okay, so I'm not having any beans. What happens if I invite 6 people to my bean party? How would I divide that among 6 people? So I have 6 cups of beans and I have 6 people. Each person gets 1 cup of beans, agree? So 6 divided by 6 is 1. Do you agree? So they get 1 cup of beans. What if I invited 3 people? What does that look like? 2 cups of beans for each person. Right? These units really are starting to matter, right? So I'm about 3 people. They each get 2 cups of beans per person. What if I invited 2 people? What would that look like? Everybody agree so far? So if I invite 2 people, they get 3 cups of beans each. 2 people, 3 cups of beans. What if I invited 1 person? How many cups of beans would 1 person get? 6. Huh. Are we okay with this? Do you see what's happening? All right. And look what's happening the closer I get to 0. My numbers are going up, right? Which makes sense that, well, and right here even, as a teacher, I'm hoping that one of my students says or does not say, You said when we divide, our answer gets smaller. 6 divided by 1 is 6. The answer didn't get smaller, Chris. How do you explain that? You with me? Because my answer didn't get smaller here. And between 1 and 0, it's going to continue to go up. So think about this. What if I invited more than 6 people? Because I'm popular, I have lots of friends. I have 6 cups of beans. What if I invited more than 6 people? How would that work? Is there anything I could do here? Partial cups. Okay. So what about this? What if I gave half cups? Because then I'm not super cheap, right? But people are still getting to eat a little bit. 6, so half. How many halves are in this? 12 half units, right? Is everybody with me on that? That half unit, making that a unit is really important. I can't say I have 12 because I don't have 12. My unit changed. You agree? So let's relate that understanding back to the bean party to this algorithm. Just kind of process it.
Okay. So welcome back. If we look at this, we can see that if those 6 cups of beans are divided by half units, I have 12 half units. I don't have 12 cups of beans. My new unit is defined as 1/2. So here I can easily see that for each cup of beans, I get 2 portions. So that's really what's happening when I'm flipping and multiplying, is I know that 1/2, that denominator tells me that each cup has 2 parts. So when I flip it, I can say 6 divided by 1/2 is 12 because each one of the 6 has 2 parts. If I divided it into fourths, then I know that each cup has 4 parts. So therefore, I would look at 6 times 4 gives me 24 fourth units, right? Not 24 cups of beans, but 24 fourth units. So if we come here and we come back to this, I drew this while you guys were away, okay? Well, not away, while you were watching the video. So here is 1 3/4 cups of beans. Right? And we saw in the video, when I worked it out, I ended up with 3 1/2 was my answer. We're gonna look at 3 1/2 what? So here is 1 3/4 divided by half units. In other words, how many half units can I get out of this? Well, here is 1/2 unit, 2 half units, 3 half units, and this is it looks like a fourth, but I have to stay with my units. I'm working on 1/2 unit, 2 half units, 3 half units, and this is a half of a half unit. So if I had real cups with beans and I had 1 3/4 cups, I could get 3 1/2 half cups of beans. That unit is so important, guys, for our population. They have to understand that 3 1/2 is 3 1/2 half cups of beans. When I leave out the unit, nothing makes sense. Nothing makes sense. If you had logged on this morning and I had blood running out of my nose and my ear was torn and my shirt was torn off, and I'm saying there's 4, you guys are going to ask 4 what? Because if it's 4 lions, then you're worried about me. I'm in trouble. But if it's 4 squirrels, that's kind of funny, right? The units matter. The units also matter here, that this is 1 3/4 divided by 1/2. it is not divided by 2. And that's what a lot of the American teachers did. They ended up getting 7/8 as the answer for this. And it's not 7/8. If we actually work it out through the procedures we were taught, I end up with 3.5, right? Or 3.5. But what's confusing is I get 3.5 half cups of beans. 3.5 half cups of beans. If I were to divide my cups by fourths, think about what that would look like. If I were to do this, what if I were having a bean party and I were giving out half cups of beans at my bean party? If I only had 1 cup of beans, how many half cups could I give out? Well, I could serve 2 people. I would have 2 half cups of beans. I wouldn't just say 2. If I have 1 cup of beans and I'm giving out half cup portions, I have to finish my unit. I have to say I have 2 half cups of beans. If I had 2 cups of beans and I gave out half cup portions, I would say I have 4 half cups of beans. And even if 3.5, and this is where that flip and multiply becomes really easy for me, is I can say that I have cups that have 2 parts each. So 3 times 2 is 6 cups of beans and 6 half cups of beans. And I have another half cup. So I have 7 half cups of beans in every 3.5 cups. Units matter. Right? This is also important. What if with whole numbers, think about what we do with whole numbers with our kids. So how many 2-cup servings can be made from 8 cups of beans? I get 4. So 8 divided by 2 is 4 2-cup servings. I think it's really interesting though when we do this. If I have 5 cups of beans and I divide it by 2-cup servings, I end up with 2 remainder 1. And remainder 1 doesn't make a lot of sense for our kids. I'm just going to be really honest. I can understand what happens here. If I have 8 cups of beans divided by 2-cup servings, I have 4 servings of 2 cups each. 9 cups of beans divided by 2-cup servings, I have 4 servings remainder 1. That doesn't make sense. A better way to talk about this is when I think about these 9 cups of beans divided by 2-cup servings, that I have 4 servings of 2 cups and 1 cup of a 2-cup serving left. I have 4 servings of complete 2 cups, that's 8 cups, and then I have 1 of another 2-cup servings. So my answer there really is 9 cups of beans divided by 2-cup servings gives me 4.5 groups of 2-cup servings, or really I have 4.5 servings of 2 cups. That half is equal to 1 cup because a full serving is 2 cups. So this is where it becomes really important for us to talk about our units and to use units. We had way more slides to cover, but we are running out of time. This is a great slide that I want you to think about. Okay, so when you're teaching, always start with the quantity. Often we mess up and we start putting it all on paper and we start trying to work out 1 3/4 divided by a half. So the first thing I do, improper fraction, then I flip and multiply, and we go through all of this procedure. And once we get to 3.5, then we go back and try to make sense of it. That's not the way to do it, guys. The way to do it is start concretely. Go ahead and put 1 3/4 cups of beans out there and ask your students, what does it mean to divide by a half? How many halves do I have in this? Make sure you continue to use your units. That mathematical structure, going from quantity to mathematical structure, is really important. The units is how we form our mathematical structure. And only after we make that first connection between quantity and mathematical structure will the symbols and what we do in the algorithms actually make sense for our students. We really want our students to be embedded with that understanding. We've written several articles, and here's some of them. around what it means to teach conceptually. I can't emphasize enough the power of the units. No matter if you're working with ones and tens or fractions, we have to start at the very basic idea of the unit, and we're going to build on it, because it's only then that the ideas of denominators and denominations make sense. So I'm going to stop the presentation here, and I'm going to open up the Q&A to see if there are any questions that you guys have for me. And I'll wait just a few moments and let you put your questions in the Q&A. So don't be shy. All right. So if you don't have any questions, I am going to put something in the chat. Oh, there's one. Yay. All right. So I'm going to put my email in the chat. And it's correct. It's pi. It's basically math 3.1415 at ymail.com. If you guys have questions, I just sent that out to, let's send it to panelists and attendees too. So 3. Okay, and then we're going to get to these questions. So the Q&A, the first one is like using hands-on and visuals. Okay, good. And so the hands-on is so important for most of our children, because, and even kids who aren't disability, it's really important for those hands-on experiences. I think we all learn better the more modalities we can involve. So I agree, Christine. Very good observation and good comment. Mark says, you mentioned Common Core, and I'm familiar with what I believe was called new math, which, as I understand, has been retracted from the teaching model. Is this demonstrating a problem with not letting teachers teach? Oh boy, that's a whole soapbox of a question, isn't it? So here's the bottom line, and this is my simple idea, my simple answer for this is, I love the idea when people say, oh, you helped write that new math. Guys, it's not new math. It's the same math Socrates taught with rocks and sticks on the beach. Right? It's the same math. Math doesn't, new math or old math, what a lot of the Common Core intended to do was to teach with conceptualization and move away from the procedures. What I find is that my students at the university love learning the new ways to think about the math, right? The ways that they had not been taught. That's usually what we mean by the new math. The way to understand all the different ways to perform a subtraction problem, or how the math actually works, instead of just being taught a set of procedures or finding multiple ways to do the mathematics. However, teachers, sometimes we're a bit more stubborn. If we've taught it a certain way for a while, we think, well, it worked. My kids got a good score, right? But do your kids actually understand it? So I've got a lot of kids that can get 3.5 as the answer for 1 3/4 divided by 1/2. But when I ask them, what does it mean? They can't tell me. So I think that's a lot of what's going on with the new math is conceptualization. That's a good question, Mark. Yeah. And is it demonstrating a problem for not letting teachers teach? I think that when teachers are teaching conceptually and the kids are getting it, it's way more fun for the teachers to teach. And I think it's allowing teachers to teach in a new and more exciting way. That's my personal answer. Right. Any other questions? I really appreciate you guys being with us today and for your time. Again, my email is there. You are welcome to send me questions or to talk. So the email address, again, I'm going to make sure everybody can see it here. Panelists and attendees. I'll type it one more time. Okay, there we go. All right, guys. I really appreciate your time today. Thank you all very, very much. Deb, I will turn it back over to you.
Thank you, Chris. That was terrific. And I don't see any other questions coming in. So we'll go ahead and end the webinar. Thank you.